All right, good morning, everyone. I saved some time and I wrote some equations that appeared already yesterday. All right, good. Right. So let me remind you. All right. Good. So let me remind you the fundamental quantity I defined yesterday. Well, I did not define it. It's Pestun who told us how to compute it. But you're dealing with some other theories called an n equal to 2 star theory. It's parameterized by a natural number, which is the rank of the gauge group, a real mass parameter, and an upper half plane variable, which is the complexify and miscoupling. And this partition function is given by the following matrix integral. It's an integral, it's not a path integral, this is a proper defined integral. It's an integral over n real variables, these A variables that parameterize the Cartan subalgebra. Some classical on-shell action, so this is really a saddle point approximation that terminates after one loop. So this is the classical action, e to the minus pi tau 2, and then this inner product, which is nothing but the killing form. Sorry, just to remind you in physics language, tau is the theta angle plus 4 pi I over gm mil squared. So this is some exponential of 1 over gm mil squared. There is some z perturbative, which is called the one-loop determinant, and it can be expressed as a product over these ratios of functions h, which are constructed out of this Barnes G function. This comes from diagonalizing the quadratic operator for this action and evaluating it on shell. And then times this object in here, which is called Nekrasov partition function, and Nekrasov partition function is an infinite Q series. In physics language, Q measures the instanton fugacity. So since in here Z appears modulo square, you're going to have instanton configuration, anti-instanton configurations, and instanton anti-instanton configuration. Another property that I mentioned yesterday, well, all of the quantities in here are actually even with respect to this mass parameter. And in particular, when you set m to 0, this n equal to 2 star theory reduces to n equal to 4. And in particular, this Z Nekrasov reduces to 1. This is going to be important shortly. Thank you. You are absolutely right. Yeah. So if you set m to 0, this partition function trivializes. So the partition function itself doesn't really contain that much information for n equal to 4. But having introduced all of these parameters, plus the parameters I mentioned yesterday, and you correctly pointed out that I didn't write them in here. So there are other parameters you can introduce. You can take derivative with respect to this parameter, and then set this m to 0, and this is going to be some non-trivial quantity in n equal to 4. And the first such quantity that we want to discuss today is this object, which I call the first integrated correlator, which is defined as taking a Laplacian, an SL2R invariant Laplacian with respect to tau, a 2-mass derivative, the logarithm of that partition function over there. And then at the end of the day, you set m to 0. So going back to Daniele's question yesterday, so one of the things, so now I'm going to give you more details about this is going to be a real analytic modular invariant function of tau. And it's actually going to be an infinite family of such functions because n is your favorite integer, let's say greater or equal than 2. So one thing we would like to understand is what type of real analytic functions are we getting out of this path integral, of this matrix model integral. Perfect. So in general, given this matrix model in here, you can write a generalized Q series expansion for this function in here. It's a sum over pairs of integers, some coefficients, a and p of n and tau 2, q to the n, q bar to the p. This contribution is what in physics we would call the n-instanton, p anti-instanton contribution. However, for this special case, note, since both that perturbative and this Nekrasov partition function are actually even functions of this mass parameter m. And since, as I wrote in here, that Nekrasov, when you put m equal to 0, reduces to just 1. Yeah, write it. And you can actually easily check that some of these coefficients vanish identically. So whenever you have both instanton and anti-instanton there, these contributions are not there, sorry, equal to 0. So this is not true in general, so the second object I will discuss tomorrow does not have this property, but this first infinite family of modular invariant functions is a little bit easier, and so it has really this expansion in here. From 0 to infinity, some coefficients, a and 0, just a function of n and tau 2 times q to the n plus the complex conjugate. In particular, let me focus now on this term, A00, tau 2, and tau 2. What in physics we would call perturbation theory. So this object in here, you derive it directly from the matrix model. Let me write it out. Equal to 1/4 L tau, and then a matrix model expectation value. I'll derive in a second. Second mass derivative of this object in here. The mass to 0, and I define the matrix model average in the following way. If you give me a function of these integration variables, aij, as in this case, the matrix model average is 1 over some normalization factor, integral over Rn, d mu a, the exponential, times the function that you want to integrate. Yeah. Oh, yes, it does. My definition of the matrix model average has a tau 2 dependence in there. Yeah. So if you want, I could put in here, this is really a function of n and tau 2. And m as well, but then you said m to 0. Yeah. Yeah, it's here. Note, since I'm only focusing on perturbation theory, this component in here is only a function of tau 2. There is no theta angle in perturbation theory. The theta angle appears, it's very important, and it appears when I start considering a and 0 with n different from 0. So to do that, I need to also include this Nekrasov partition function, which does explicitly depend also on tau 1. But for now, I just want to focus on the 0-0 sector, perturbation theory, and it's only a function of G and Mills. But the only G and Mills dependence is in here, from the matrix model point of view. Don't seem convinced, David. Okay? And sorry, this normalization factor, you just define it in such a way that if you insert 1, the matrix model expectation value is 1. At this point, yes, I cannot do that. there is a nice integral representation for this object. The second mass derivative of this perturbative part, this product of h functions, you set m equal to 0, write it in terms of some function, which in the literature is called k prime. And this k prime admits a nice integral representation. Minus the integral between 0 and infinity, w, cosine w z 1 divided by the sinh square of w in dw. I don't know if people have played with this sort of integrals. So you have a 1 over sinh square kernel, and you can integrate, and the momenta of these measures are odd zeta values. To 2k plus 1, zeta 2k plus 1, minus 1, k plus 1, z. So if you expand this object out, you're only going to find single zeta values. This is the first exercise that I want to set. You can do it by pen and paper, but if you can use Mathematica or PariGP, that's a little bit easier. So exercise. For n equal to 2, so SU2 n equal to 4, super Yang-Mills theory, we can evaluate this A00 to tau 2, which again, I read it from there, is 1 over 4 tau 2 square d tau 2 square. Noticing here that although I brought a Laplacian with respect to tau, there is no theta 1, sorry, there is no theta dependent, there is no tau the 1 dependence from this part in here. So this Laplacian is only this derivative in here, acting on the expectation value of this k prime of A12. So you can take this integral representation, put it into this expectation value, and do the integral, and you're going to find that this object is asymptotic to 9 zeta 3 divided by pi tau 2 minus 225 zeta 5 divided by 2 pi tau 2 square plus whatever, 2205 zeta 7 divided by 2 pi tau 2 cube plus order tau 2 to the minus 4. So the asymptotic expansion at the cusp for this first integrated correlator is producing only rationals times zeta values when I expand it in terms of pi tau 2. This is actually true for any number of colors. It's not just true for n equal to 2. Of course, yeah, so absolutely, thank you.
So there are two types of things.
Yeah. So in here, I'm just focusing on this A00. I still need to consider all of the AN zeros over there, yeah, with n different from 0. So those are all going to be instanton contributions, yeah. Okay. in general, for every integers, this 800 tau 2 expanded at the cusp. Contains only rationals times odd zeta values. And so we actually do have a proof of this statement. There are some beautiful results due to Don, Zagier, and Harer using matrix models. And you can actually show that for any number of colors, the asymptotic expansion of this object contains only zeta values. Basically, it comes from this integral representation in here. Yes, already here, amongst the infinite dimensional world of real analytic modular invariant functions, this first integrated correlator is very special. Its asymptotic expansion at the cusp produces only depth 1 multiple zeta values, which is a funny way of saying just odd zeta values. Oh, sorry. I can move it here. Just an excuse to see what's in there. Oh, there's nothing. Oh, that's very sad. All right. Good. Right. Good. From this fact in here, with Michael Green and from Cao Wen, we actually conjectured an expression. It's a lattice sum representation for this whole function. Let me write it out and then comment. So this is just given by a one-dimensional lattice sum of two-dimensional. Between 0 and infinity, e to the minus t pi m plus n tau squared over tau 2 times function of n and t in dt. Let me make a couple of comments. The whole Yang-Mills coupling dependence is here. And the all n dependence is in this family of functions here. Now, for the people in the audience who know what I'm talking about, this looks like the Borel transform of something. And I'm using as coupling constant this lattice combination in here. So, another exercise for the students. Let me define this theta, tau and t. The notation is not random. Although I'm not sure if someone is going to be talking about these objects. What is someone? So this is an indefinite theta series. It's a sum over the lattice of the exponential of minus t pi, the modulus square of n plus n tau over tau 2. And little exercise show that for every t, let's say positive, so you don't have any issue with convergence, this object is modular invariant. This one looks like a theta lift of something. I'm going to say a few more things next lecture. This is a very convenient lattice sum representation for this object. This function Vn of t, but first we just conjectured the expression. We computed this Fourier coefficients for n equal to 2, 3, 4, then we spot some patterns. And then we use these results by Zagier and Harrer on matrix model to actually prove that this expression is correct. This has some interesting structure. These functions in here are just some rational functions. There are some polynomials, n of t, divided by t plus 1, the 2n plus 1. And this Pn of t are some rational coefficients, palindromic polynomials. Of degree 2n minus 1 without constant terms. For example, for SU2, this integrand is a rather simple function. T minus 10t squared plus 3t cubed divided by 1 to the 5th power. Sorry, palindromic means that the coefficient of the lowest term is equal to the coefficient of the highest, and so on. So this lattice sum representation, first of all, it's completely not obvious from the matrix model. There is no lattice sum to begin with in the matrix model. There's also something not to be expected in general. Not every real analytic function admits a lattice sum representation. So going back to your question, somehow this n equal to 4 selects a very small class of the infinite dimensional world of real analytic modular invariant functions. Not only this object will admit a lattice sum representation, also the object I'm going to talk tomorrow admits a lattice sum representation. More complicated. The object that I'm going to be talking about tomorrow, you're also going to encounter products of zeta values. But again, only zeta values. So there must be some vector space. We don't really understand how to mathematically define it, but this object, this n equal to 4 produces a very small world. Yeah, yes, please. Yeah, sure. No, yeah. Yeah. So the other thing we thought about, so this object in here looks like something which are called Hilbert series, if you send t to minus t. And this suggests that you're somehow counting something, but we don't really know what we are counting. Yeah. Very good. Yeah. So I'm going to write it in a second. There are some other properties. First of all, we find that you might be worried in here. So normally, when you introduce lattice sums, especially for Eisenstein series, you avoid the point n equal to m equal to 0. In this case, if you put the point n equal to m equal to 0, this exponential factor is gone. So you might worry about convergence, but this integral is actually finite. Second thing that you can show is that if you take this polynomial and you divide it by square root of t, this object vanishes for any n. Lastly, what David just said, that this object has an inversion property. Sorry, I'm saying these are things that we noticed. Shortly, I'm going to give you an alternative tool to study this type of modular invariant functions in here, which is called SL to Z spectral analysis. And you can actually show from the spectral decomposition that passing to the lattice sum, you have to satisfy all of these properties. Yeah.
Just once again.
Yeah. Correct. with a very special measure. So in this case, the measure is just a flat measure of the 4 points. Yeah. The one I'm going to be talking about tomorrow, the measure is a bit more complicated, is this D111 function that you know. Yeah. So what you can do, we actually did it. You know the unintegrated correlator up to 5 loops. You take the work of... At recoupling. At recoupling, exactly, yeah. So you take the correlator that Paul and friends gives you, you integrate against this measure, the first few loops, and you will see that you get exactly these numbers in here. The annoying thing is that up to 3 loops, the correlator itself is actually planar. It does not. It only depends through the 't Hooft coupling, so it's only n GML square. Yes, exactly. Yeah. From 4 loop onwards, no, you start having non-planar corrections. So, yeah. So over there you see the independence, but for the first 3 loops, you don't see any independence. Then you take the same quantity and you integrate it against this other measure, this D11. You take again the F graphs, you integrate it, and you produce a wilder class of numbers, which are not still insane. They're at most product of all zetas. But these are, as we were talking before, these are the only numbers you seem to produce. The correlator itself is going to contain a lot of additional, let me call it garbage. When you project with this measure, it selects very special numbers. Yeah.
I'll give you another example. In general, identical structures.
Yeah.
But I found
yeah.
close it to a 3.5.
Yeah, and then
multiple polynomials.
Absolutely.
So an integral of a horrible.
Yeah, could produce something very nice. Yeah. Thank you. Yes, please. Yeah, very good. Give me a second. Yeah, thank you. Yeah, you can do that. This is very much related to the spectral representation I'm going to be talking about in a second. Yeah. Good. And then, if you didn't know this property in here, you could still do the following. That's an exercise. Show that given this lattice sum representation, necessarily Bn of t is equal to T inverse Bn of T inverse. Of course, if you know that this is palindromic polynomial, it's exactly what you were saying before, David. But actually, you can prove it directly from the lattice sum representation over there. And the hint I can give to students is that whenever you have these sort of lattice sums, you might want to do Poisson resummation. If you do Poisson resummation enough times, you can actually show that this must be true. Another thing that I invite the students to do from these lattice sums, again, it's fairly easy to extract the coefficients an that I wrote before, an0. So if this expression holds, then a00 of n and tau must necessarily be the sum over, let me call it n hat, or integral between 0 and infinity, e to the minus I tau 2 e n hat square times square root of tau 2 e, this function bn of t in dt. A little exercise in Poisson resummation. And at this point, you can do what Enrico was suggesting. You can expand this function in here at small t. Integrate term by term, perform the sum over n hat, and you're going to find precisely an expression of that form. You're going to find that this object is an asymptotic expansion of this type. Sum for s to infinity, zeta of 2s minus 1, I tau 2 to the 1 minus s, and some rational number that depends on n and s. This is actually how we first found this function Bn of t. We computed this matrix model, 800. You get these numbers, and you try to rewrite them in terms of that lattice sum over there. That lattice sum is the zero mode. Sorry, it's not a lattice sum, it's just an infinite sum. It's the zero mode of this object in here. Very good. No, at this point, so once we convinced ourselves that was correct, what you do, well, you bring a lot of data to Don, and it tells you to compute a generating series, which we did. You do the generating series over n, all the number of colors, and then you can actually show that this object, using the results of Zeige and Harrer, must satisfy a differential equation. Yeah. What you can actually do then with this differential equation, you can find the solution to the differential equation, and then you can extract the n equal to 2, n equal to 3, n equal to 4 terms, well, any n, and we show that our expression was indeed correct. Yeah. So rather than focusing on n equal to 2, 3, 4, you construct a generating series, use this matrix model technology to derive a differential equation just from the matrix model, and then from there you're pretty much done. Yeah.
You discovered this.
Mm-hmm. Yeah. Another thing that you can do from this lattice representation is yet another exercise in Poisson resummation, and you can find what I called before the k-instanton sector. If the lattice sum representation, this object must equal the sum over m and n integers, such that m hat times n is equal to k. You bar to the k, and then this integral. Now, if you have ever played with real analytic Eisenstein series, this is usually what you do when you try to construct the Fourier expansion of the real analytic Eisenstein series. So from a lattice sum representation, you do some Poisson resummation, and then you integrate this object term by term, and you produce some Bessel function. Yeah. 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 So remember that I told you that in this first case, you do not get this PQ contribution. You only get the instanton or the anti-instantons.
Okay, right. So,
yeah. Yes, exactly, yeah. So very good. For the next, the second integrated correlator is much more complicated, and you also get the Q instant, P instanton, Q anti, sorry, MP instanton, anti-instanton. Yeah, thank you. Yeah. So yeah, the first thing we did, we conjectured the lattice sum representation. We use these perturbative coefficients to construct this function B, and then we can read off this Q instanton sector. And then you go back to the matrix model and use this Nekrasov partition function, and you can actually check that the things are the same. Yes. Very good. Well, eventually this leads to the conjecture. But so what you do is the following. There is no proof that is constructive. So Zeige and Harrer tells you how to construct these cumulants from the matrix model. There's some generating functions of 1, 2, 3-point functions. And this is really for the generating series. You don't specify the gauge group. You're integrating over an n-dimensional Hermitian matrix model, and you do the sum over n. You can actually show that this cumulant satisfies some sort of 3-terms recursion relation. And this 3-terms recursion relation eventually leads to what I wrote yesterday, that Laplace difference equation. So at this point, then you know that this integrated correlator must satisfy this Laplace difference equation. The only thing you need to do is a recursion relation, so you can evaluate the matrix model for n equal to 2. For n equal to 2, it's fairly easy to evaluate it brute force, so you can actually show that there's that form over there. And then at that point, this is your seed from the Laplace difference equation. You put it there and you find it for all n. And so one thing that I didn't say, because it's not really relevant, So these polynomials in here are constructed out of Jacobi polynomials. Jacobi polynomials satisfy a three-term recursion. That's precisely the three-term recursion of Zagier. Yeah. Again, sorry? Yes. Yeah. You do the calculation you can calculate the matrix model for n equal to 2 exactly, because for n equal to 2 Nekrasov partition function, you can actually write it very explicitly. For n equal to 3 and higher, although there are expressions for Nekrasov, they're not for all instantons. So you can do one instanton, two instantons, three instanton. You can convince yourself that this expression is correct, but I wouldn't claim that that's a proof. But then you bypass it entirely. I constructed for you the n equal to 2 matrix model results, and then using Zagier-Harrer, I proved that this is the starting seed of this Laplace difference equation, and then you write it in this way, and you get this recursion. Good. So, excellent. So at this point, yeah.
Oh. You have a sum of
Mm-hmm.
and you
Yeah.
so
Absolutely. Yeah, but the fact is that in this way, so okay, this is the full lattice sum representation that makes it immediately invariant under SL2Z. So first of all, you see immediately the SL2Z invariant. And then again, if I want to actually check if this is correct from the matrix model, the matrix model naturally leads me to considering the 0 instanton sector, the 1 instanton sector. So I need to have a way to extract this information from the lattice sum. And this is what I give you in here. So the 0 mod sector is just given by that integral over there. And the k instanton sector is given by this integral here. But you see that once you have fixed this function, Bn of t, the two things are clearly related. But from the matrix model, they come from very different objects. The 0, 0 only cares about this Barnes G function. But for any instanton sector, I need to put this Nekrasov partition function. So in principle, the two things have nothing to do with one another. But clearly, modular invariance links the two things. Because if you give me a modular invariant function, a real analytic modular invariant function, the 0, 0 sector and any instanton sector, they're not unrelated. They must talk to one another. But going back to what Enrico was suggesting before, you can try to do something fairly silly from here. And you can directly expand this integrand and do the integral term by term. So this leads to some formal expression of this real analytic object in terms of some nicer real analytic objects, which are called real analytic Eisenstein series. So what you could do, so from here, first of all, I can integrate the n equal to m equal to 0 term and isolate it. That's just a constant. We call it whatever, C. And then I'm left with this sum. And at this point, you can expand in Taylor this function, integrate term by term, and you're going to get an expression of this type. They call the coefficient. Yeah. Here. Yeah. Exponentially suppressed by that. So there is a singularity of that integral, but the Borel singularity is at -1. Yeah. Let me not write an equal sign here because this right-hand side is absolute garbage. It has no convergence whatsoever. It's not a power series. It's a formal manipulation. Oh, I forgot which convention I'm using here. There's probably some gamma factor. If you actually do this integral, it produces divided by 2 half. This object is called the real analytic Eisenstein series. For this to be convergent, really, you want to have real part of S to be greater than 1, but actually you can extend this one to a function over S complex. Yes.
That's the thing we saw in S.
Very good, yes. Yeah. In here, from this point of view, you don't get the half integral once, you get a formal infinite sum over integer index Eisenstein series. It's going to be a big difference when shortly I'm going to be talking about the large n expansion. If I take this integral, and before evaluating it, I expand at large n, I'm going to get a power series in 1 over n corrections, whose coefficients are going to be rational linear combination of half integral real analytic Eisenstein series. But at finite n, I can do the integrals that Enrico was suggesting, and I get this infinite sum of integer Eisenstein series. Now, this equal sign in here, what it's really telling you is that you would like to use what is called SL2Z spectral theory. This infinite sum is really the spectral representation of this lattice sum in here. This is what I want to talk about next. It's another useful tool to deal with this sort of objects. So, let me erase the board. I'm going to say some fairly basic concepts of spectral theory. I would invite you to look at either Herra's book or Iwaniak. But the key idea is the following. We want to compute, well, we know that we are dealing with an SL2Z real analytic function, and we want to write an L2 normalizable function, modular invariant, so if you want on the fundamental domain of SL2Z, as a linear combination of nicer functions. Which functions do we pick? We pick eigenfunctions of the Laplace operator, of the hyperbolic Laplace operator. So what it means is that if you give me a function from the upper half plane into C, which is modular invariant, f of gamma tau is equal to f of tau, then you should be able to write it as a sum over some coefficients times a basis of function. This is what you usually do in linear algebra. You pick a nice basis of function, you compute some inner product, it projects your function onto the nth basis element, and you write this linear combination.
Why do you keep putting in that?
Very good, because it's not going to be a sum. Thank you. Yes. Very good. So the reason is that what are these eigenfunctions of the Laplacian? Very good. So first of all, what's the inner product? That's what is called Peterson inner product. The integral over the fundamental domain, f tau, g tau, complex conjugate, d tau 1, d tau 2 over tau 2 squared. So a function is in L2f if inner product with f is infinity. Now, L2f splits into a bunch of eigenspaces of the Laplacian, the constant, the continuum part of the spectrum, and the discrete part of the spectrum. Let me talk about these three different spaces. The first part is really nice. I hope I don't need to convince you that if I take the constant function, that's L2 normalizable and is a solution to the Laplacian with eigenvalue 0. Fantastic. That's the first part. This constant property here, that's precisely this term. The continuum part of the spectrum is a little bit more interesting. Is the span of the real analytic Eisenstein series that I wrote over there with the real part of S equal to a half. These objects in here satisfy, apologies to the mathematicians, I'm using the opposite convention for the Laplacian, but whatever. So this function in here satisfies in general the Laplacian on S tau is equal to minus, let me write it like that, S, 1 minus S is star S and tau. This is true for any S complex, but the L2 normalizable real analytic Eisenstein series are the ones that are living on the critical strip, real part of S equal to a half. The discrete part of the spectrum is something very interesting on its own, and I'm going to say extremely little about it, because this object in here are these so-called mass cusforms. Let me denote them as mu n of tau. They satisfy Laplacian in tau of mu n equal to some eigenvalue minus lambda n, mu n of tau. And these eigenvalues are of the form a quarter plus some positive number, Tn squared. And these numbers in here are a bunch of seemingly random numbers. So conjecturally, the spectrum is non-degenerate, so at one eigenvalue you have at most one mass cusforms. And these Tn are a set of sporadic real numbers. You can go on the LMFDB, the L functions and modular functions database, and you can actually check some of these numbers. You click on mass cusforms, you order them by the spectral parameter, and you will see that the first mass cusform, this eigenvalue T1, is 9.533, and so on. There seems to be no rhyme or reason behind these numbers. There appears to be beautiful patterns, but they really seem to be a set of random numbers. The important thing about these mass cusforms, which is going to be important shortly, is that they are purely, in physics language, they are purely non-perturbative. At the cusp, they decrease exponentially fast. So these mass cusforms must take the following form. They're given by a sum from k equal to 1 infinity. Numbers, let me call them beta k, and they depend on the cusforms. And then you either have the cosine of 2 pi k tau 1 or the sine of 2 pi k tau 1 times square root of tau 2 and the second kind Bessel with index I Tn 2 pi k tau 2. First of all, a little exercise for the student. It's actually very easy to show that the most general solution to this Laplace equation, that is exponentially suppressed at the cusp, must take that form. Only the Bessel function is basically a solution to the homogeneous problem. It is exponentially suppressed. Yeah. Sorry, very good. This is the index of the Bessel function, and is I times Tn. And Tn is precisely the spectral parameter, this random number. Okay. Yeah. There's two types. Pretty weird. Yes. So there's two types of objects. This one is invariant under tau 1 goes to minus tau 1. This is called even. This is instead odd. This first value I was writing here is for an odd one, actually. If you want an even one, I think the first value is like a 14 point whatever. Yeah. These coefficients in here, which again, you can find tabulated on LMFDB, are again a set of seemingly random sporadic numbers. Yeah. However, thanks to this fact in here, I can give you another exercise. These mass cusforms do not appear in here. Let me keep this expression. So first of all, what is this? So now to go back to David's question, what is the right way of writing this equal sign? Well, the idea is still that one. These three pieces form a basis of L2 normalizable eigenfunctions of the Laplacian. I'm going to write every L2 normalizable real analytic function, modular invariant, as a linear combination of the constant piece, the continuum part, and the discrete part. So this goes under the name of Rölke-Seiberg. Seiberg, sorry, not Seiberg. Decomposition. can write f of tau has f inner product with the constant plus an integral over the critical strip of f inner product with the Eisenstein series times the Eisenstein series plus an infinite sum over all the mass cusp forms, the inner product of f with the cusp form, the cusp form. Yes, yeah, remember, over there I was writing a sum over all my bases. The basis of the continuum part of the spectrum is parameterized by S real part equal to a half. So the sum over all of these eigenfunctions becomes an integral over S. This is why over there I had to write an equal sign in quotes. You see, I don't have a discrete parameter labeling the continuum part of the spectrum, I have a continuum parameter. But I'm still doing exactly the same thing. In quantum mechanics, think about this as scattering states. You are summing over the scattering states. Yeah. Yes, very good. Yeah, that's sometimes how you write it. That's true. Yeah. That's pretty much the same thing you're doing. Which basis of eigenfunctions you're choosing here? The Hamiltonian is the hyperbolic Laplacian on the fundamental domain. Yeah. Good. However, luckily for us, exercise. Given the lattice sum in there, you can actually show that the inner product between this first integrated correlator and the mass cusp forms is vanishing. So in this spectral decomposition for Cn, i.e., the spectral decomposition for this first integrated correlator does not contain these mass cusp forms. I should say there are very important cases coming from physics. For example, if you study two-dimensional partition function for CFTs, there are some really nice work by Eric Permuter, who have shown that many of these weird aspects of 2D CFTs, for example, chaos, are pretty much intertwined with the presence of these mass cusp forms. The fact that these numbers seems to be random numbers implies some chaotic properties of the underlying partition function for 2D CFTs. Luckily for us, this object does not contain these mass cusp forms.
It's orthogonal to the crazy.
Yeah. Very good. Good question. Yeah. Already for the second integrated correlator, the class of function I'm going to be dealing with is slightly bigger, but they're still related to this Eisenstein series. Most definitely, there are going to be mass cusp forms over there. Yeah. We still don't fully understand what the role is from a physics point of view. Sure. So the example I'm going to give you tomorrow, if you expand it at the cusp, it still has perfectly good numbers. In the perturbative series, zetas, product of two zetas, that's it. In the instanton sector, rational and zetas. The spectral decomposition will also contain these random numbers. Somehow, when you take these infinite sums in the Selberg decomposition, when you put all of them together, you're only going to get these nice numbers. I have no idea how that happens. Yeah. The problem is that we tried in some ways to deal with this part in here. For example, for this, what I'm going to mention tomorrow, this generalized Eisenstein series. The problem is that you really need to have analytic control over these mass cusp forms, which we don't. We do not know what these numbers are. As I said, if you go on LMFTB, you find like some significant digits, but it's most definitely not, or conjecture is not a rational number. Same for these coefficients. Now you're giving me an infinite sum of these objects, and you're asking me what is the coefficient in front of tau 2 to the minus 1 at the cusp. I cannot tell you analytically, yeah, using this method. Yeah, that's a very good point. And perhaps a hint for this part, because I'm not sure if this is something that is usually done, but this is a useful tool to deal with this sort of lattice sum. The lattice sum I brought before can actually be recast in the language of a Poincare series. And whenever you're dealing with this sort of integrals and you have Poincare series, there is a pretty nice trick, which is called the unfolding trick. So hint. If you go back to the integral representation I gave you before, I introduced this indefinite theta series, theta of t and tau. Let me subtract the term coming from the n equal to n equal to 0 term. So that term I factorized it out. That's just a constant. I don't care about that. So this object in here, you can actually write it as a Poincare series. It's a sum over gamma in gamma infinity SL to Z of some function gamma and tau with phi a periodic function. This is why you need to remove the stabilizer of the cusp. Gamma infinity are the t transformations, plus or minus 1 and 0 plus or minus 1. So by writing the lattice integral in terms of this Poincare series, then you should be able to do the following. Use the unfolding trick. If you don't know what the unfolding trick is, exercise, check what the unfolding trick is. And you can show that this integral, which is pretty much what this is, with a mass cusp form, must vanish. The idea is that by doing the unfolding trick, instead of integrating over the fundamental domain, you're going to be integrating over the strip. But integrating over the strip, you can, and you use this Poincare series. This function in here is periodic, while instead the expansion of the mass cusp forms as this cosine or sine. So when you integrate cosine or sine over the strip, you're going to get 0. This is only true in this case because the Poincare seed can be chosen to be a periodic function of tau. For the function I'm going to be telling you tomorrow, first of all, we do have some expressions for Poincare seeds, but they will not have this expression here. So over there, you know that there's going to be some mass cusp forms. Yeah. Good. Continue running, should finish at 45. Very good. Perfect. All right. So at this point, we have various different tools to analyze this first integrated correlator at finite n. But the thing I'm interested in, again, if I want to connect with string theory, is taking the large n limit. And at large n, the decomposition I brought before in terms of Eisenstein series with integer index will actually change. And it's going to take some more interesting form. And again, interesting from a physics point of view. And we encounter, again, a very small space of real analytic functions. So at large n, so we are not performing, for the physicists, we are not taking the truth limit. This, we are still keeping tau to be in the upper half plane. We send the number of colors to infinity. And so using this generating series technique that I was mentioning before, let me just write the result. We found this asymptotic series, so I should really write it. Well, I'm going to write the full trans series, but whatever. So it's given by some term, n squared plus 4, which is clearly a modular invariant function. But then we get an asymptotic series in 1 over n, in half integer powers in 1 over n, multiplied by some coefficients, which are going to be real analytic modular invariant functions of tau. But they're not going to be random real analytic functions of tau. Each order, we have a finite sum with rational coefficients, not particularly important, times half integer Eisenstein series, real analytic Eisenstein series. I think here I'm using, well, let me use the same convention. However, again, whenever in physics you send some parameter to infinity, you might also worry about the presence of non-perturbative corrections. But now the parameter I'm sending to infinity is n, so I might still expect to find non-perturbative corrections in n, something that does not emit a power series expansion, but they still should be functions of tau. So we were able to find these objects, and again, they lead rise to a very small world of real analytic functions. These functions in here, let me write them out. Again, there is a power series expansion in corrections in 1 over n, but now the coefficients will be, again, some rational numbers, multiplying some real analytic functions, which are going to be exponentially suppressed in n. So this function b, let me write it out, is given again by a lattice sum. Not unthinkable, given that the integral at any given n was given by a lattice sum. But the fact that the world that we are landing on in this world is represented by lattice sums is very interesting from a physics point of view. Good. So let me bring it up. Good. So this new function dn, s, and tau, they clearly are non-perturbative in n. There is literally an e to the minus root n at exponent, so there is no way for you to expand this in a power series at large n. It's exponentially suppressed. It goes to 0 together with all of this derivative with respect to n. But given the fact that it's given as a lattice sum, it's clearly a modular invariant function. So first of all, let me say a couple of words on the physics for the perturbative coefficients in 1 over n, which goes back to your question from yesterday. So the physics at large n and tau fixed, I computed this quantity starting from this matrix model formulation of n equal to 4. But in this limit, this should be equivalent to some calculation that you should do in this 10-dimensional type 2B superstring theory. And this 1 over n expansion corresponds to what is called the alpha prime expansion, or low energy. So terms in the perturbative expansion at 1 over n should correspond to terms that we find in type 2B when studying the scattering of 2 gravitons into 2 gravitons. And actually, we can understand some of these terms. The first term does not depend on tau. And remember, tau in string theory is the axiodilaton. The first term over there corresponds just to Einstein-Hilbert. So superstring theory in type 2b, 10 dimension, at low energy is just 10-dimensional supergravity. The overall number multiplying the Ricci scalar is just a number, and that number is spec C2 1/4, whatever, not interesting. More interesting are the 1/n corrections, and these 1/n corrections, they correspond to higher derivative corrections in type 2b. Type 2b starts with supergravity, but since it's type 2b superstring theory, you're going to get superstring corrections. The first of such corrections that were computed using completely different methods is a particular contraction of the 10-dimensional Riemann tensor, actually 4 powers of the Riemann tensor. Yeah. No, good. So I'm not doing a 't Hooft expansion. Tau is fixed. I'll write the dictionary. I'm not doing the. You're thinking also about doing gravity loops. I don't want to do gravity loops. I'm doing superstring theory. So tau is fixed. So I'm gonna get an I'm gonna write in a second. I'm gonna get an expansion of the low energy expansion of type 2b. Technically, of course, it's in AdS 5 cross S5. It's not really flat space, but let me forget that for a second. You compute type 2b low energy. You're getting Einstein-Hilbert plus alpha prime cube, some function of the axiodilaton, this 4 contraction of the Riemann tensor, plus whatever is the next order, 4, plus you get an infinite tower of corrections to supergravity, right? When you map the parameter alpha prime to n, this order in here corresponds to looking at the order n to the alpha in this expansion in here. And the coefficient that you find over there is E 3/2. This was computed by Mike Green and Good Perle. Completely different methods. No, there is an well, there are in here. Remember, this is tau. No. This has G-string corrections inside. I can write them out.
No, but the first term.
Yeah. This was the last comment I wanted to make. So, what is this one? Is zeta 3 tau 2 to the 3/2 plus zeta 2. With some factors of pi that I'm not going to be careful about, minus a half, plus non-perturbative terms. So you see there are a couple of genus corrections in here. It's not just 3 level.
No, I've seen the first.
Oh, this one, yeah, all right. But in here I'm writing that as a function of tau.
Huh?
In here I'm writing as a function of tau. So there's also this object in here. You're just focusing on this one.
Yes.
Yeah, then it's 3 level, I agree.
And then...
Yes, absolutely, yeah. Very good. It's not obvious. Excellent. Thank you. So, okay. There is no Q&A session today, though, right? All right. I can tell you a little bit more about that. So you're absolutely right. You can, from that, you see, the fact is that that expression is SL to Z invariant, so it contains everything. What I can do now, I can actually compute from there the 't Hooft expansion. You need to rearrange the series. You need to write the Eisenstein series in terms of its Fourier mode, and you can do it. And then there are what you're more useful to think about, the genus expansion in lambda 2, but a strong lambda. Yeah, absolutely. Yeah. And perhaps the last thing I want to say, so sorry, then the next order, this one, this object in here, again computed by Mike, is this Eisenstein E 5/2. and is the second order in there. And then you might think that this object is Eisenstein, okay, the pattern, you don't need ChatGPT, 3 halves, 5 halves, 7 halves. That is incorrect. This object is not an Eisenstein series. This object will appear tomorrow. It's called a generalized Eisenstein. Yeah. Lastly, these non-perturbative terms for the physicists, they actually correspond to PQ string worldsheet instantons. They're really some sort of saddle point of the action, and we can get them from here. Very good. So let me stop in here. So tomorrow I'm going to be talking about the second integrated correlator, which is a little bit more interesting. Yeah.